Can I pause you for just a minute to make sure that we're all on the same page with part A? So part A is it's asking to find the force of gravity, that's Fg, right? And what was the equation that we came up with the equal sign, thanks to Cavendish? What did we come up with? What is it? So you got your masses, right? You got your two objects. Remember, because we said, and we've been saying for so long, that the gravitational force is the force between two massive objects, right? So we got two of them. One of them is, oops, I was going to highlight that. It did not work out well for me. I'm going to try that again. One is the satellite, and one is the Earth. So those are our two masses. We've got a radius that is twice this big. So it's 6.38 times 10 to the 10 to the 6th. Does that make sense? Multiply that by 2 because that's what we're talking about for our radius. And then don't forget to square it. A lot of times, friends, when we get mixed up with FG, it's because we forget the square. So don't forget that square. What did you get for a value for part A? What is it? 4,900 newtons, or 4.9 times 10 to the 3rd newtons. Are we all okay on that? Ish. I don't have my numbers written down, so I'm banking on you guys. Are we in agreement though? Is that, yeah, we've got some agreement? All right, so now you're trying to figure out how fast it's going. We don't know how long it takes for it to go around. In fact, that's what we're looking for next. Let's think about this force. If this is the Earth, here's the Earth down up here, and here's my satellite right here, and it's going around in a circle, what force is acting? What forces are acting on the satellite? Force of gravity. In fact, we just found it, didn't we? Fg. So we could write down an F-net equation, F-net for the satellite, and friends, we really like to write those F-net equations. Even if it's simple to remind ourselves of what's going on. Net force is all the forces acting. How many forces are acting? It's Fg, isn't it? And if there's only one force, what do we know has got to be happening with this satellite? It's got to be accelerating. So we know it's ma, but oh my gosh, we also know that it's orbiting in a circle, which means that the acceleration is what kind of acceleration? Centripetal. And so we could write this even one more time. We could say Fg is equal to m times v squared over r, right? Because v squared over r is a sub c. Yeah? We derived this a long time ago. We did this a long time ago. It was before we took our final and all of that. But it's there. You can use this then to solve for v, right? And then use that to find your period. I'm going to let you keep working for a minute. Does that sound all right? Do your thing. We'll talk in a minute. Yeah, what's up? Yeah, of course. Hold on just a sec. Let's do it.
Yeah.
Sounds like we just need some chewing on of numbers here. All right, so let's go through this just to make sure that we all have the right numbers. Because, you know, numbers are interesting and good, so we want to make sure we're okay. So, again, we have Fg equals mv squared over r. Is everybody okay with this statement here? So then we're trying to solve for v. How fast does it go? So algebra-wise, we're going to do what? Fg times r divided by m square root the whole deal to get your velocity? Yep. What number do we get when we do that?
5,790. 1,900,000.
Anyone else want to help me out? 5,600. So 5.6 times 10 to the 3. Did I hear you right? No, 2. 3. So possible reasons that might not have gone well. One would be forgetting to do like exponents. The other one, and this one I do want to make sure, because this is not a trivial question, is there's only one m here. There are two m's here. And it's not just like we're just going to randomly pick one. You have to use your physics brain to figure out which one. So when we're doing this, we're saying, okay, there's a force between any two objects with mass. Boom, boom. This right here, this is the net force acting on which object?
The satellite.
The satellite. We could draw a free body diagram for the Earth too, right? We could. What's that? picture, it would just have an arrow going that way. Right? That's all it would have. It's all good. But this is the one we're talking about because this is the one we're talking about with our centripetal acceleration, with our circular motion. So if and when you're dealing with a problem like this, the game is that you want to say, and we've done this before, but sometimes we forget. Here's the acceleration. Which object is experiencing this acceleration? That's what I want. So I want which mass here?
2000.
Just the 2000. This right here is the mass of the satellite. Question? Or
Force of gravity shared between both. Could you say also that the Earth experiences centrifugal motion because of the satellite, but the acceleration is so small because the mass is so big?
so yeah, I'm going to do two pieces for that. Is that okay? So let's talk about that. That's a really good question. So first of all, let me ask a quick question. Does the satellite pull on the Earth?
Yes.
Yes.
Which pulls harder, the satellite or the Earth?
Equal, yeah.
The forces are the same, aren't they?
Trick question.
It's not a trick question. It's a make sure you understand physics question, right? Two masses, it doesn't matter what order they're in. They're just multiplying two numbers. The force is going to be the same on the satellite and on the Earth. Who's going to accelerate more, though?
Satellite.
Definitely the satellite, because this one's times 10 to the 24th. That's a little bit bigger than times 10 to the 3rd. Right? 24 is bigger than 3, right? Like, yeah. So this one's going to accelerate a whole bunch more. Now, does this one orbit, does this one experience centripetal acceleration? Yes, but it's very slight. Now, I'm going to take that a step further real quick. Is that okay? Because sometimes we have two objects that have about the same amount of mass. Okay? If we have two objects, please pay attention, you guys. This is important stuff. You have two objects that have about the same center of mass, or about the same mass, They're both going to pull on each other. And if they're both given a little bit of velocity, then they will orbit one another. Yeah? Do we know what we call this kind of a system when you have two stars that do that? Binary system. A binary system is a system with two stars that orbit each other. We are not in a binary system. A lot of cosmologists, what's that? Cosmologists, not to be confused with cosmetologists. Okay? Cosmologists are people that study the origins of the universe, study the origins of space in general. Okay? A lot of people that study the origins of our solar system believe that we were close to being a binary system. Where's our other star?
The sun.
The sun is our star.
Where's
Where's the other one? Jupiter. Jupiter is, it's not quite the size of the sun, but if it had been just a little bit bigger, it would have been big enough to ignite nuclear fusion at its core. And if it ignites nuclear fusion at its core, then it would be a star. Okay? And then we would have a binary system of two stars that orbit one another. Okay? And in fact, what do they orbit? This goes back to our rotational stuff, friends. What do they orbit? They orbit one point. Where's that point? What's that radius? The center of mass. So if you have two stars that are the same mass, it would be right in the middle. If you have two stars that are, one is bigger than the other, which is the way it usually works, we have two different orbits, one that's small and one that's big. Okay? In fact, let me say this one thing and then I'm all there. Jupiter and the sun kind of orbit, it's a little bit of that wobbly thing. But the center of mass of that system of just those two objects, the sun and Jupiter, the center of mass still is inside the sun, just barely. So there's a little bit of wobble that happens from just those two. It's also a little funny because, we got those other planets too. But Jupiter is huge compared to all the other planets. Okay? Question?
Yeah. Well, I was at the National Air and Space Museum.
Yeah.
Like last
Whatever.
Monday, whatever. Yeah, and they had a little display on that.
Yeah.
Wow.
They showed a little video, like what it
Very
looks like.
cool.
Looking at the wobble. Now, stop. We don't need this. Okay.
Wow.
The other thing that I wanted to share is that from our perspective and in our experience, one sun is the way to go, right? Like that's just how it is. Most stars, I think it's something like 85%, but don't quote me on that. But I think it's something like that high. Most stars exist in a binary system. Most stars exist in a system where you've got two stars that are orbiting a common center of mass. We are very, very unique in the fact that we only have one. Okay? And there are planets that orbit these binary systems. If they orbit inside, they do these kind of like crazy figure eight patterns. Otherwise, they just orbit the common center of mass much wider out. Okay? It's one of the few things that, from a scientific perspective, that Star Wars got right. On a lot of the other planets, when they're doing like this, big pan shot, they'll show two stars, right? Because that's what it would have looked like. And so the idea of night and day is very different on those planets as opposed to here. Well, they might, but it might be a very short night, or they might have like a super bright part of the day and then like a moderately part. What does that mean really? But yeah. So anyway, that was a long explanation, but I wanted to make sure that makes sense, that those forces are the same. How fast is it moving? It's moving kind of fast, sure. How long does it take for the satellite to orbit the Earth? How do you think? Oh, sorry, go ahead.
I didn't get that answer. I thought we were going to go.
Oh, I'm sorry.
That's okay.
Yes, we can totally go over it. I kind of started and then I got distracted. I apologize. So we plugged in. So 4.9 times 10 to the third. And then the radius is twice this thing, right? 6.3 or 6.38 times 10 to the, was it sixth? Is that right? 1, 2, 3, 4, 5, 6. But we're going to multiply that by 2.
All right, got it.
Are we okay?
Yes.
All right, sweet. Is everybody happy? Okay.
So why do you still multiply that by 2 then? If it's,
Because it's just it's the radius of the orbit. Center to center. Did that make sense or did that confuse?
yeah, I forgot that it was, I thought it was like just
Yeah.
Yeah, we're good.
How do you find how long it takes? What do you do, Nick?
Velocity equals negative
So this is part C. Velocity equals omega r. I don't know omega.
omega is equal to 2 pi over 3.
Okay. Yeah? How long does it take? What do we get? Is there a value? Did I make it a value? For period? Or no? Did I confuse somebody? Did I confuse people? I may have. It's possible. Ian, you look really perplexed. Kian, did you get an answer
Oh,
for the period?
wait.
I think what the velocity.
Oh, did I? Oh, I did. You're right.
It's like 14,342 seconds.
Yes.
Okay. T is equal to, oh yeah, I did. You're right.
It's like 4 hours.
What'd you, 4 hours-ish?
Yeah.
How many
it's like,
seconds? 4 point what?
1.43 times 10 to the 4th.
1.43 times 10 to the 4th?
Ish.
Ish. Okay. Is that okay?
That's pretty good.
All right. We've got a few minutes. In those few minutes, I am going to have you start working on something. Okay? The sheet I'm going to give you, can we move on? Is that okay with everybody? I'm going to give you a sheet. It's kind of like Mad Libs, but it's not because it's actually notes about electrostatics. A lot of this you have learned. You've probably learned most of this information in prior science classes. If you haven't, that's okay. That's why we're doing it. Okay? I want you to fill out the front of this today. I'll give you some time in class today to work. If you get stuck on the questions, you can refer to pages 550 through 555 in the purple science or textbooks that are over there, or these are the pages in your book at home. Does that make sense? Because I don't have extra of the AP texts, but all of this stuff is the same no matter which book you look in. So I'm going to give you about 5 or 10 minutes to work on this now, and then we will put this away, but I want this front side done before you come back tomorrow, or before you come back on Monday, okay? Not tomorrow. I won't be here tomorrow either. All right, so why don't you send somebody up to grab these and get started?
I will get them. Give me one.